Alright, so we've seen in previous discussions that the binomial probabilities are well approximated by the normal curve or the Gaussian curve. In other words, if we take the binomial, which is sometimes just written binomial with n tries with each experiment having a success rate p, and we were to draw a plot of that, we saw that there was a little histogram. We make a histogram of the probabilities. So here I'm probability plotting p of k, the probability of having k successes in n tries, and this is centered around mu, which is np, and it has some width, some characteristic width, which is given by the standard deviation, which was the square root of npq. And we saw that as n went to infinity and p stayed fixed, this was well approximated by a continuous curve, which was given by the normal distribution with the same mu and the same sigma of z. And in fact, if we wanted to know the probability of the number of successes being between the number of success being between b and a, we saw that that was approximated well by the integral from a to b of this function sigma z dz. Now here I've suppressed the things we discussed, like the continuity corrections and normalizing this to be a standard normal. I've just written in terms of this normal mean with sigma. But somehow implicit in our discussion is the idea that a and b are somewhere here in the middle of this curve. They're not way out here. We're not talking about an a and b out here. That's a different kind of question, and it's related to what we want to talk about today. So this is fine when n went to infinity and p stayed relatively fixed. So then, when that case, what happens? Mu grows, which is np, but it's much bigger than sigma, which is equal to the square root of npq. Remember, q is equal to 1 minus p. So it's this relationship is that mu is much bigger than sigma. Now, what if we pick a binomial where that's not true? So let's think about a binomial with parameters. Let's say we pick n to be 10, and let's pick the probability to be 1/10. So now, mu is equal to np, which is equal to 1, which is actually equal to, which is, well, approximately equal to the square root of npq, which is just about 1 also. I mean, it's not exactly 1 because q is a little bit less than 1, but it's more or less 1. So now, all of a sudden, sigma is comparable to mu. And if we look at the picture, we notice something looks different. It looks much more like this. So this is 1, this is 0, this is 2, this is 3, this is 4. And here I'm writing pk. It's much more, it's asymmetric, first of all. It doesn't look symmetrically centered around the mean. And it has a whole bunch of values right around 0 and 1, and then it falls off very quickly. And if we draw another picture, if I now plot the binomial with n equals 100 and p equals 1 over 100, so once again, I've kept mu to be 1 and sigma just about 1, it looks very, very similar. It looks something like that, something like that, something like that, something like that. In the book, they have a whole bunch of plots, and they start to look quite similar. So if we then looked at the binomial with 1,000 and 1 over 1,000, we would get a very similar picture. Now before, remember, the mean was running off to infinity, this standard deviation was spreading out, and we had to renormalize things to pull it in, but here the picture looks pretty much the same, and it's staying very discrete. All right? Now, this kind of limit, when we're letting p be very small and n be very large, is a different setting, and the normal central limit theorem doesn't work here. So the central limit theorem is not applicable in this range, because what we're thinking about is very rare events. So we're thinking about rare events. So whenever you think about see something where it's a rare event, the chance of success is very, very small, And of course that has to mean that, relative to the number of experiments you do, which is another way of saying that the mean, mu times p, is something small, and sigma is also about the same order. Well, then there's a different type of limit theorem, and that's called the Poisson limit theorem, and that's what I want to talk about now. So let me erase the board. Okay, so the Poisson limit theorem, or approximation if you want to the binomial, is in the setting, so it's always going to be in the setting where NP, which is the mean, is something comparable to sigma, which is square root of NPQ. And more formally, we're thinking of a sequence of p's, so think of it such that n times p is converging to some number mu as n goes to infinity. So we're constantly changing the experiment. First we have a box where we have some few number of black balls and mostly white, and then we add a lot more balls, but we keep the fraction of n times the probability, the number of black balls, constant. And then we ask, well, what happens as n grows very large? Well, let's see that by exploring. So if we define P and K to be the probability of K success in n tries, well, let's think about what happens to Pn 0. So the probability of getting no successes as n grows. Well, that's just q to the n, so 1 minus p to the n. Now, since we're assuming that p is getting very, very small as n gets large, we can use the Taylor series approximation of e to the minus p, and say that's approximately 1 minus p plus some higher order terms. So we'll just replace this 1 minus p with e to the minus p. So this is approximately e to the minus pn. And since we're assuming that np goes to mu, so we're thinking about a whole sequence of these problems, I should really have a little n here, then this is approximately e to the minus mu. So in this case, we see that the chance of having no success is approximately e to the minus mu for large n. And now, to see what happens for other integers, other small integers, let's define the odds ratio that we already defined before as Pn over Pn minus 1. If you write that out for the binomial, that's just n minus k plus 1 over k times p1 minus p. And we can rearrange that by just multiplying through and factoring things around to np over k times 1 minus k minus 1 over n. I should have little subscripts n everywhere on these, divided by 1 minus pn. Now, as n gets large, pn is going to 0, so the denominator is going to 1. And the numerator, as n gets large, k is fixed, and so n over k over n goes to 0. And so this whole thing is approximately np, which is just mu over k for n large, because we've assumed that Pn is going to 0, so that n times Pn is approximately equal to mu. That's our assumption. Well, if we use that fact, and if we're interested in computing pkn, that's just Pn0 times r, we should have an n here of course, Rn1 times Rn2 all the way up to Rnk. That's just telescoping. In other words, if you think about it, since this is just the ratio, the first one here, this one is really just P1 over P0. The P0 cancels, and I'm left with P1, and then the same thing happens all the way up until I'm just left with PK again. And now, if I use the approximations we figured out, the first one being this one, for P0, we get e to the minus mu. And now for each of these, I use this approximation, which I just figured out. That's mu over 1 and then the next one is mu over 2, all the way up to mu over k, and that's equal to what? E to the minus mu. I have k mu's, so that's mu to the k, and then the bottom I have 1 times 2 times 3 times 4, that's k factorial. So what I've discovered is that this can be approximated, so pk, if I erase this here, in this setting is approximately e to the minus mu, mu to the k over k factorial. And this approximation in the setting when np goes to mu, and n is large, and therefore sigma is approximately mu, it's also, this is called the Poisson approximation. Of the binomial. All right. One thing we'd like to just make sure is that this new approximate value actually is a probability distribution, and it is. We give it a name. It's called the Poisson distribution. And the probability under this distribution, the Poisson distribution with parameter mu, of having k is equal to e to the minus mu, mu to the k, exactly this number we found here. And just to make sure, so this is a distribution on, we have to say it's on 0, 1, 2 to get its range all the way out, so all the positive integers including 0. So we just want to make sure this number, well, it seems to be a good distribution on those numbers. It's positive, and the only thing left to check is does it sum to 1? Because we want that 1 equals, that's a question mark, the sum k equals 0 to infinity of p mu k. Well, let's see if that's true. We plug this in, and we factor out the mu, e to the mu out in front, and I'm left with the sum k equals 0 to infinity of mu to the k over k factorial. Now we sum all of these. So what we're saying is that this is the Taylor series for e to the minus mu, so e to the minus mu times e to the minus mu is equal to 1. So just to recap, we want to check to make sure that this was a good distribution, that it summed to 1, and we did that by summing all the probabilities pk. So finally, we have talked about the Poisson distribution, which is a different approximation for the binomial in a different setting. It's in the setting where n times mu is going to a constant as n gets very large, so n times p is going to a constant mu as n gets very large, so pn is necessarily becoming very small. So this is what happens when you want to approximate rare events. That is to say, a setting where the number of experiments are such that the problem is big, but the probability is so small of success that the chance of success is rare. And this is different than the Gaussian approximation, which is a different approximation to the binomial, which is when we're talking about a more typical number of successes. When we have enough experiments and the probability of p is not so small that it's somewhere around the mean, a few standard deviations around the mean. In this setting of the Poisson, the mean and the standard deviation are very similar, whereas in that normal approximation or that Gaussian approximation, the mean is much bigger than the standard deviation.